Welcome to this course on Elements of Mechanical Engineering, where we are studying the energy sources and basics of thermodynamics. We are in the first module. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. And today we are going to see the definitions and terminology that are related to thermodynamics. Okay, now we'll go to the first slide. So the first definition we are going to study today is system. So whenever we are studying a thermodynamic system, we have to know what are the basic terminology related to the thermodynamics. When we study a particular object or a device which is undergoing a thermodynamic study, we have to consider a particular system. Okay. Now whatever the object we have taken into consideration for the thermodynamic study, this object is called as system. Now I will draw a. So this is a universe where the entire universe is taken into consideration, and in the universe I have a system. So this is a system which is of my key interest for the thermodynamic study. Now in the universe, the area apart from the system is called surroundings. This is surrounding. Now, apart from the system, the remaining thing is called surrounding. This entire thing, the system and surroundings are separated by a layer called boundary. Now, this is called boundary. Now, what happens is this entire thing, the system, surroundings, boundary, all these things will be inside the universe. Okay, so this is universe. Now let us see the definitions that are related to system. First of all, the system, a portion of universe which is under investigation. Okay. When we are studying a body thermodynamically, we have to consider an object. This object inside the universe, which is separated by a real or imaginary boundary layer, is called as a system. Now the boundary layer, which could be real or imaginary, this will separate the system from surroundings. Okay. Now, let us take an example of the system. A portion of test tube where reaction is taking place can be called as a system. Whereas if we take a small test tube where we will do some experiments, like in chemistry, this test tube can be called as a system, and the area surrounding the test tube can be called as surroundings. And we are staying on the planet Earth. This can be called as a universe. Now we'll go to the next definition, that is surroundings. The rest of the universe which might be in a position to exchange energy and matter with the system is called surroundings. Now we have seen we have universe inside which we have a system which is separated by a boundary layer from the surroundings. Now, again, I am repeating the definition. We have a universe inside a system is there, which is separated from the surroundings with the help of boundary layer. Now, all these things comes under a single definition that is related to the terminology of the thermodynamics. Now, when we study the definition of surroundings, it is the area inside the universe apart from the system which is in a position to exchange energy and matter. These two are the key things. The surroundings in the surroundings in the universe have the capability of exchanging energy and matter with the system. So simply we can say, if I have a system, if the system is generating some work, this work can be taken out by the surroundings, or some work can be done by the surroundings on the system. Okay, work can be given out of the system or it can be taken into the system. And again, heat, some amount of heat can be supplied to the system or heat can be taken out of the system. Okay, so the surrounding has the capability of transferring or exchanging the matter and energy into the system or out of the system. Now boundary. The third definition boundary goes like this. The system is separated from surroundings by a boundary which may be real or imaginary. So the layer that is separating the system from the surroundings, this could be a real boundary or a imaginary boundary, but any kind of boundary should be there in order to separate our system from the surroundings, and this is called a boundary layer. Now we'll go to the next definitions that are related to system. So far we have seen a system. There are different types of systems are there, that is isolated system, closed system and open system. Now we'll see what is an isolated system. Isolated system is one that can transfer neither matter nor energy. So isolated system indicates there is no transfer of energy or matter with the surroundings. We have seen we have a universe inside which a system and surrounding will be there. So when the system is not able to, or it will not try to exchange the energy or matter with the surroundings, then the system can be called as isolated system. Now, so this is first kind of system. There is no transfer of energy or matter. And the second kind of system is closed system. In this, the boundary is sealed but not insulated. So we have a closed boundary here, but it is not insulated. Therefore, a closed system is one which cannot transfer matter but can transfer energy in the form of heat, work, radiation, and into different forms from the system to the surroundings or from the surroundings into the system. Okay, so this is the second kind of system. So this closed system will have the boundary. It will have a closed boundary, but it will not transfer any energy. It cannot transfer energy. It can transfer, it cannot transfer matter, but it can transfer energy, like in the form of heat, work, and radiation. So it can give the radiation, work, or heat from the system to the surroundings, or it can take in reverse also. Okay, it can take the heat, work, and radiation into the system also. And the third one is open system. So open system is the one which both energy and matter can be shared with the surroundings. We can transfer matter and we can transfer energy also into the system or out of the system. Okay, anything can be done in an open system. There is no boundary. Still, it is considered as a system, but it is called as open system. Here the boundary is there. Very thin boundary will be there, which is separating. For maybe it can be called as a imaginary boundary, where it will separate the system from the surroundings, but both energy and matter can be transferred in and out of the system. Now we'll see what is an equilibrium. So in any system, equilibrium has to be there. Whether it is a chemical equilibrium, mechanical equilibrium, or thermal equilibrium. Okay. Equilibrium, the word itself indicates the state of balance. It has the direct meaning as it has the equilibrium. If any system is studied, when the system is under balanced condition or static condition, then it can be called as a system under equilibrium. There are no unbalanced potentials within the system. Unbalanced potentials means there should not be any unbalanced loads or unbalanced chemicals left over for the reaction to be happened, or unbalanced heat or work. They should not be there. Unbalanced potentials should not be there in the system. Then that system can be called as, is said to be under equilibrium. So there are different types of equilibriums, that is chemical equilibrium, mechanical equilibrium, and thermal equilibrium. Now we will see what is chemical equilibrium. If there is no chemical reaction or diffusion of the matter from one part of the system to another part, the system is said to be in chemical equilibrium. When there is no chemical reaction happening in the system, then it is said to be chemical equilibrium. So the system should be very stable in forms of chemical reactions. And then second one is mechanical equilibrium. If there are unbalanced forces in the system, then the system is said to be, if there are no unbalanced forces, then the system is said to be mechanically equilibrium. Suppose I have taken a system where I have applied some 10 kgs of load, and in the opposite direction I am applying the same kind of load. Now the system can be called as a stable system, or the system is said to be in the equilibrium, because I am applying the same kind of load on all directions. The loads are balanced here. So that is why there is no unbalanced forces. Then this system can be called as under mechanical equilibrium. Okay, there should be no unbalanced forces. Mechanical equilibrium. And coming to third one, which is of our key interest now, we are studying the basics of thermodynamics in this module. So the thermal equilibrium is of keen interest. When a system is prevailing in chemical and mechanical equilibrium, is separated from its surroundings by a diathermic wall, and if no spontaneous change in property of the system is said to be in state of thermal equilibrium. Okay, now I have a system. So far we have studied different types of systems, open, closed, isolated systems. I have considered a system where the system is not giving out any heat or not doing any work. That means I am not saying this it is an isolated system. I am considering this system when all the thermal quantities, all thermal potentials are unstable, or unbalanced thermal potentials are not there, then this system can be called as thermal equilibrium system. Okay, so we have studied all the three types of equilibrium. Chemical, where there are no chemical reactions, the chemicals are very stable. And in mechanical equilibrium, when there are no unbalanced forces, the system is very stable, then it is said to be under mechanical equilibrium. And then thermal equilibrium, it is where there are no unbalanced thermal potentials like heat transfer, work, enthalpy, internal energy, work, etc. There are no unbalanced potentials. These heat, enthalpy, entropy, etc. will be there in the systems, but they are not unbalanced. They are completely balanced. Then the system can be called as under thermal equilibrium. Now we will go to the next set of definitions. So this is properties. Any thermodynamic system will have some properties. So these properties will define the state of the body or the system. Suppose I have taken a system. If I want to indicate or explain the state of this system, I need some properties to indicate how the system is, what is the state of the system, what is the condition of the system. To explain that, I have to have some properties. So there are two types of properties in thermodynamics. They are intensive and extensive properties. First of all, we'll see what is an extensive property. An extensive property of a system is that which depends upon the amount of the substance or the substance present in the system. So there are some properties which depends on the mass or the amount of substance present in the system. Then it is called as an extensive system. Suppose we can take the example of an extensive system like volume or mass. Suppose I have taken a system, it has contained some mass of air inside it. So the mass, volume or energy will directly depend on the substance present inside the system. So it will depend on the mass of the system. Okay, the volume itself depends on the mass depends on the volume, and energy of the system depends on the mass of the contents inside the system. So these are the extensive properties which depends on the substance present in the system. Okay, how much amount of a substance is present in the system, it will change or vary the values of these properties like mass, volume, energy, heat capacity, enthalpy, entropy, free change, etc. So these are all the extensive properties. So these can be called as dependent properties. They depend on the amount of substance that is present in the system. And second one is we have intensive properties where these will not depend on any kind of quantity or amount. Okay, these are independent of the amount of substance present in the system. Some examples are temperature, pressure, density, viscosity, refractive index, surface tension, and specific heat. These are all the intensive properties. They does not depend on the quantity of matter present in the body, amount of substance present in the system. Okay, they will does not depend on the amount, so they will be anywhere. They will be taken as same. Like temperature, in the entire system, the temperature will be same. Okay, if I divide this system into small parts, now if I study each and every part, like if I take this part and this part, the temperature will be same because it does not depend on the amount of matter present inside the system. So at these 2 points, the temperature will be same, but the volume or energy may not be same at these 2 points. Okay, like here the volume will be different, here the volume will be different. It depends on the amount where it is present inside the system. Okay, whereas the temperature or pressure, density, viscosity, these does not depend on the amount of material, and they are same in the entire system. Okay, so this is about the extensive and intensive properties. Now we'll go to the next set of definitions. So we are studying the thermodynamic properties, where we have to understand there are some processes, path, cycle. So these are some basic terminology related to thermodynamics, because when we are studying a thermodynamic body, it may undergo some kind of state change. It may change from one state to another state, maybe from solid to liquid. Now, in order to change its state from one to another, it may undergo some kind of transition. Now, this transition can be named in different processes, like it can be named in different ways. Like there are 3 types of transitions are there. That is, first one, path, process, and cycle. In path, if all the changes of the states of the system are plotted, then line joining the change of state of the system is known as path. Suppose if I have a pressure versus volume diagram. So this is PV diagram, where I will plot the points where the pressure and volumes are changing from one state to another state. And suppose I will take the example of water. If I want to change the water from solid to liquid form, I have to increase the temperature, or I want to increase the pressure so that the volume will increase. So this can be showed like this. I will increase the pressure and volume so that the water, solid ice can be converted into water. So in the PV diagram, this line which is showing the change of state, okay, it is changing from state 1 to state 2. Now this line or curve is called as path. Okay, and the second one, process. What is a process? A process is a complete description of change of state of a thermodynamic system throughout a specified path. So whenever we are studying a thermodynamic change of state, where we will use some set of path. Suppose I will take 2 kinds of path change here. This is PV diagram. I will start from point 1 and I will go to point 2, and from here, this is path 1, and from here I will go to point 3. This is 2 to 3. Now what happens is, this entire process of change of state, that is from 1 to 2 and 2 to 3, combinedly can be called as a process. And then third one, cycle. What is a cycle? Cycle is a process where it indicates the initial state is equal to the final state. Okay, suppose if I have a cycle here. Now in the same diagram, I have started from point 1 and I have reached to point 2, where it has changed some state, and from there I have changed from point 2 to point 3 and it has changed another state. Now I have returned this from point 3 to point 1, where it has reached the initial state. I have started at point 1. I have gone all the way up to 3 and I have returned back to point 1. And now the final state of the system is exactly equal to the initial state. Now this kind of process is called a cycle. A thermodynamic cycle is defined as the series of state of changes such that initial state is identical with the final state. So these are another set of definitions. Now we will see different laws of thermodynamics which will guide the study of thermodynamics. So there are 4 laws. Zeroth law. Zeroth law is very simple. If 2 thermodynamic systems are in equilibrium with a third system, then the first 2 systems can be said to be in equilibrium with each other. Simply I will draw a diagram. I have 3 systems. Say system A, system B and system C. Now, if the system A and C are in thermal equilibrium, they both have the same thermodynamic properties. The values of properties are same. And the properties of thermodynamic properties between B and C are also same. So, A and C is in thermal equilibrium, B and C are in thermal equilibrium, then A and B also can be called as under thermal equilibrium. This is the first zeroth law of thermodynamics, where we will compare 3 bodies. When A and C are in thermal equilibrium, B and C are thermal equilibrium separately, then A and B are said to be in thermal equilibrium because both of them are in thermal equilibrium with a third body, that is C. Now we'll go to the first law of thermodynamics. That is second definition in this slide. Energy can neither be created nor be destroyed, but it is transferred from one form to another. So energy can neither be created nor be destroyed. This is also called as the law of conservation of energy, and the first law of thermodynamics deals with that, where energy is converted from one form to another form, but it is not destroyed or created. Then we'll go to the second law of thermodynamics, where the entropy of an isolated system always increases. The entropy of an isolated system. We should know what is entropy. Entropy is nothing but the change in degree of disorderness of the system. Degree of the disorderness of any system can be called as entropy. When there is entropy of an isolated system, it will always increases. If I take an isolated system, the entropy will always increases. Okay. For this, I can take an example of an empty room which is kept without cleaning for a longer period, like 1 month. Now, what happens is all the dust particles will accumulate in the room, and the room become more messy day by day. So, after 1 month of period, when the room is kept not cleaned, then the room will have more entropy. Okay. Now, if I try to clean the room, the entropy I have to apply from the outside will be increased, and the entropy inside will decrease because I am arranging the particles in a regular manner. So, if an isolated system is there, its entropy will always increase. And the third law of thermodynamics is the entropy of a system approaches a constant value as the temperature approaches absolute zero. So, the entropy of a system approaches a constant value when the temperature approaches absolute zero. What is an absolute zero temperature? It is nothing but the 0 degree kelvins is called as absolute temperature, or minus 273 degrees centigrade. So this is the temperature where any known electronics will not work up till now, because the research has been still going on. People are trying to design the electronic devices to make them work at this temperature or beyond this temperature also. As of this textbook is written or this course is taught, there are no electronic devices or circuits which are possible to be working at a temperature of minus 273 degrees centigrade. So that is why this is called as an absolute zero temperature. When the system, the entropy approaches a constant value when the temperature approaches absolute zero. Okay, that means when a system is very cooled, like up to minus 273, there is no change in entropy. entropy will be constant. Now we will see some of the thermodynamic properties. Now the thermodynamic properties are the properties which are used to indicate the condition of a system or indicate the state of a system. Now what is temperature? Temperature refers to the degree of hotness or coldness of a body. If I want to tell a system is hot or cold, I have to sense it with the help of a thermometer. Okay. If it is cold, I will feel the cold with my hand, or if it is hot, I will feel the hotness. So, in specific way, it is the way of determining the kinetic energy of the particles within an object. So, what happens is, if a body is hot, all the particles inside will be moving randomly, moving fastly. The kinetic energy of all the moving particles will be very high, which indicates the temperature is very high. And in contrast, when the kinetic energy of all the moving particles is very low, the temperature will be low. So this is how the temperature is defined in sense of kinetic energy, where faster the movement of the particles, more the temperature, and vice versa. So this is the basic definition of temperature. It is the degree of hotness or coldness. And the second definition is enthalpy. Enthalpy is a measurement of energy in the thermodynamic system. The quantity of enthalpy equals to the total heat content of the system, equivalent to the system's internal energy plus product of the volume and pressure. So enthalpy is nothing but it is equal to internal energy plus product of volume and pressure, U plus PV. So this is enthalpy, capital E. So enthalpy is the total amount of energy present in the body. Next, entropy. Entropy is nothing but the degree of disorderliness of a system, and this is represented with U. Okay. Sorry, this is represented with S. So entropy is always represented with capital S, and entropy is nothing but degree of disorderliness of a system. So it will indicate how randomly the particles or the molecules that are arranged inside a system. So that can be taken as entropy. And next definition is internal energy. So an energy from inherent in every system is the internal energy, which arises from the molecular state of motion of matter. The symbol U is used for the internal energy, and the units of measurement is joules. Okay. So what is internal energy? Any system will have some internal energy. It will be stored in the body, stored in the system. So this is the internal energy which is inherent of the molecular state of motion. So whatever the molecules inside a system will be moving with certain speed. So this speed will create some energy. This energy is considered as internal energy. Now the internal energy is taken as, it is referred with the symbol U, and it is measured with the units joules, and it has a formula that is delta U is equal to Q plus W. Q is nothing but the heat supplied into the system or out of the system, and W is nothing but the work done by the system or work done on the system. So this is the definition, internal energy. And then we have work. What is the definition for work? Work is nothing but thermodynamic work is one which the principal processes by which a thermodynamic system can interact with its surroundings and exchange energy. So what is thermodynamic work? So we have two different definitions related to mechanical engineering. One work is related to mechanical engineering. We can define work as force into displacement, force into distance. This will give you the work, because some amount of energy is applied in the form of force to move an object through a displacement from one place to another place. So the displacement is D and force applied is F. The product of F and D will give you the work done. Whereas in thermodynamics, the work done definition is different. Here we will calculate the work done with the help of this formula, minus P into delta V, where we are applying some pressure on a system and the volume will change. So the change in volume is represented with delta V, and the pressure is taken as negative because we are applying some pressure on the system. So W is equal to minus P into delta V. So this is the work done in the sense of thermodynamics. This is work done in the sense of mechanical engineering, that is solid mechanics. And next we have some processes which are used in thermodynamics. They are adiabatic process, isochoric process, isobaric and isothermal process. Now we'll see in detail what is an adiabatic process. An adiabatic process is where no heat transfer into or out of the system occurs. So in adiabatic process, there is no heat transfer. When a system is undergoing a change of state from one to another state, in that process, there is no heat transfer. Then the system can be, the process can be called as adiabatic process. Okay, there will be no heat transfer into the system or out of the system. This can be called as an isolated system where it is following a certain process. Now, in the adiabatic process, in the graph we can see we have this line, this curve is there, which is going from point 1 to 2. This curve representing the adiabatic process. Okay, there will be a decrease in the pressure as well as there is an increase in the volume. Okay, pressure decreases, volume increases. So this is adiabatic process. And the second one is isochoric process, a process where no change in volume occurs. Isochoric representing there is no change of volume when the system is undergoing a process. In the second PV diagram, we can see initial point is this one, final point is this. So it is undergoing a constant volume process. So because of this, there is no area under the curve. If we draw a line, there is no area under this curve. In the first case, we can draw lines from point 1 and 2, and this will be the area under the curve. So this indicates some work is being done by the system. So in adiabatic process, there will be work, but there is no heat transfer. Whereas in isochoric process, there is no area under PV diagram, which is indicating that there is no work done by the system. Okay, there is no work in isochoric process. Coming to the isobaric process, here the pressure is constant. Pressure is constant here. So this is initial state and final state where we have some work done here. This can be calculated with the help of a constant pressure value and volume. So P into V, we will get the work. Okay, we have seen in the previous slide the formula for work is minus P into delta V. So here there is a change in the volume, but the pressure is constant, even though we have some work done here. Because see this yellow color part, this entire part is indicating the work done. Okay, now we'll go to the next definition, that is isothermal process. Isothermal process is the one in which there is no temperature occurs. Okay, in this there is no temperature changes. Okay, temperature is very constant. Okay, so this blue color curve is indicating the isothermal process where it is undergoing some kind of pressure volume changes. So whenever there is work is being done on the system, the work can be calculated by using these graphs. And in the isothermal process, the pressure will always decrease and volume is increasing when the volume is increasing. And we can calculate the work done under this PV curve by using this area. This yellow color area is nothing but the work done when the process is going from point A to point B. Okay. Now these are the set of definitions which are useful while we are studying the thermodynamic systems. And then we'll study what is a thermodynamic cycle. The next definition is thermodynamic cycle. Whenever there is a process which is the initial state is equal to the final state, then it is called as a thermodynamic cycle. Okay. Now in this PV diagram we can see here the cycle is going from point 1, 2, 3, 4. Okay. Between point 1, 2, 3, 4 there is a constant. Some things are constant, some parameters are constant and some parameters are not constant. They are increasing or decreasing, they are taken into the system or taken out of the system. Now we'll see, we have taken the example of a air compressor and combustion chamber. So here point 1, 2, between 1 and 2 there is a compressor where we will take fresh air and we will compress. So while compressing there is one process, okay, the pressure will increase. And between 2 and 3, we will add some fuel to this compressed air and we will make the combustion happen. Now between 2 and 3, there is some heat addition done to the system. That is, heat is added to the system. So this is shown in the form of Q in, okay, between 2 and 3. And after 3 and 4, there will be an expansion, that is increase in the volume and decrease in the pressure, okay, between 3 and 4. So whatever the hot gases that is coming out of the combustion chamber will be sent onto the turbine, and the gases will expand on the turbine. Okay, between 3 and 4, the pressure will decrease, pressure drop will be seen, and volume will increase. And after 4 to 1, where we will collect the exhaust gases coming out of the turbine, and these exhaust gases will be sent back after processing into the compressor, and they will be reused. Okay. Now, when we take the condition of air here, first it is fresh air mixed with some kind of old exhaust gases. Now it went to compressor, after that it went to combustion chamber, after that it went to turbine, and after that it came out of the turbine as exhaust gases, and these exhaust gases are again sent back into the compressor. Now, we can simply understand from this cycle, between 1, 2, 3, 4 points, the air is moving from one state to another state. It is undergoing some kind of chemical reactions, and it is again being bring back to normal. So this entire thing can be called as a thermodynamic cycle, where we can simply observe that initially the air is in the air form, it is in the gaseous form, and it underwent some changes, and finally it came back to its original state. Now this is thermodynamic cycle. So these are some of the definitions and terminology that are related to the basics of thermodynamics, and we will meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.